So, good morning, everyone. So first I would like to thank the organizers for inviting me to this program and to this conference. I think it's been really fantastic so far, and it's a wonderful place to be here. It's my first time, actually. So now during this talk, I try to give you an overview on advances in modeling emission lines, in particular in the optical and UV, in cosmological and galaxy simulations, and I also will try to discuss to what extent this can help us to move towards a more meaningful, fair comparison to spectroscopic observations and also help with their interpretation. So I guess in this room, it's kind of needless to say that emission lines are incredibly important probes for ISM conditions and ionizing sources in galaxies. Thanks to James Webb, we have now really for the first time these large samples of emission line data from galaxies out to cosmic dawn, which, for example, allowed us to discover a new population of faint low-mass AGN above redshift 4-ish, where, however, the census, the fraction of these AGN is still somewhat debated, also because it's very hard to actually identify AGN where we're not having a clear broad component like in hydrogen or helium lines. There are also indications that ISM ionization conditions, as we've heard, are very different in high redshift galaxies compared to local galaxy populations. But if you really want to, fully understand of how the early chemical enrichment proceeded in our universe, we need reliable metallicity estimates, which is somewhat challenging if we're not having auroral lines detected, such that we cannot just apply the direct temperature method. I mean, of course, we can use some SED fitting tools, statistical Bayesian fitting codes like Beagle bagpipes in order to estimate some physical quantities from observed emission lines, but also there we're making some simplifying assumptions, have some uncertainties and degeneracies between different free parameters. So now an alternative way, which can also contribute to the interpretation of emission lines, is via forward modeling numerical simulations into the observational space. And this way, potentially, possibly, to get a better or additional control and handle on these various uncertainties, degeneracies which are there, and actually also account directly for selection effects biases in the simulations. So this is the main focus of this talk, and this implies that we need to model synthetic spectra and emission lines for numerical simulations. So to explain that, let me briefly group them into two big classes. On the one hand, high-resolution simulations, which roughly capture the multi-phase interstellar medium structure, meaning individual elements where emission lines are produced. On the other hand, we have cosmological large-scale simulations with good statistics, lower resolution, where we're not really resolving line-emitting regions. If we first have a look at high-resolution, mainly radiation hydro simulations, capturing multi-phase ISM, and if you look in literature, there has been achieved significant progress over the past few years, like, for example, modeling line emission on the fly via Ramses RT and the PRISM model applied to dwarf galaxy simulations. This is still something computationally very expensive, so I guess Holly, talking after me, is going here more into detail. We can also model line emission for these type of simulations in post-processing by basically coupling individual gas elements to a photonization code like cloudy or mappings in order to get the ionization state, compute the emissivities. This has been done, for example, for the Sphinx simulations, Sarah simulation, and there are a number of, I think, very interesting and exciting projects ongoing. We are also in the process to, develop an emission line generation tool for high-resolution radiation hydro simulations, capturing an ISM structure, capturing individual massive stars, supernova explosions. This is done in collaboration with Tim Ratjen and Steffi Walch at Cologne University, where we take advantage of silk simulations of stratified disks. So here you can see some first results, showing emission line maps for different optical lines like H alpha, H beta, where you can nicely see individual H2 regions emerging. And we also plan to actually apply this type of method to our new set of high-resolution radiation hydro simulations of dwarf galaxies, where we will have additionally component, like whole AGN component, meaning we can also capture the line emission from a resolved narrow line region. And with these type of, let's say, comparably accurate or sophisticated simulations, we can, for example, study what could be the contribution from the diffuse ionized gas to the total line emission, so relative to what comes from H2 regions, narrow line regions. With our preliminary results from SILP, we do find impact on optical line ratios, meaning it may affect the location of a gas patch in the BBD diagram. We're trying to quantify that, which may also be useful for interpreting observed emission line data. But now this type of emission line modeling, even if being comparably accurate and sophisticated, I guess it's the most accurate what we have at the moment, these type of simulations are suffering from low statistics. If you think of zoom simulations, they have a very limited redshift mass range, partially not even a cosmological context, like on this slide. So for the rest of the talk, I want to now turn to how we can employ also these, new large-scale cosmological simulations where we have excellent statistics, model line emission, and try to, help with interpretation of observed emission line data. Now, the problem we're facing here, as I briefly mentioned before, is that we're not really resolving cold-warm ISM phases. We're not really resolving individual H2 regions or something like that. This is the same for all major codes, all major simulations like TNG, SIMBA, Magneticum, EAGLE, and so on, meaning modeling line emission has to be somewhat more approximate, okay? But since I started to work in this field, I think there has been really an explosion of different, groups trying to do that. I've listed here some of them, also using different simulations. But the basic concept behind is always the same. So they start from large grids of photonization models done with cloudy or mappings, connect them with cosmological simulations, basically by matching some of the free grid parameters to physical quantities predicted by these simulations, be it on a particle basis or in a galaxy-wide fashion. And so this way to basically assign a synthetic spectrum with emission lines to a simulated galaxy. And essentially this has the advantage of reducing the large free parameters grids of parameter space of model grids to more physically motivated combinations as predicted at a given redshift, right? And we were among the first developing such a tool. And what we do is that we populate a simulated galaxy with H2 regions with the same galaxy-wide ISM properties, but different star cluster ages. So in practice, what we're doing is that we're convolving line emission from individual H2 region models with a constant star formation rate history for stellar populations younger than 10 megayears. Okay? So there's some simplifying assumptions, but it turned out to work very well, and our model also uniquely includes line emission due to AGN, post-TGB stellar populations, and fast radiative shocks. Now, in general, these various methodologies which are out there in literature, compared to what I've shown you a few slides before, have now the big advantage that they're incredibly efficient, computationally inexpensive, easily applicable to large galaxy populations within a cosmological setting. We can easily explore also, the impact of different ionizing spectra, making different assumptions in the photonization models. And we have, for example, our method applied to a variety of different simulations, semi-analytic models like TNG, Santa Cruz SAM, Gaia SAM, just to name a few. And now when we look at predictions for these various different methodologies applied to different simulations, then they seem to be consistent with some basic emission line properties of low redshift galaxies, like line luminosity functions in terms of H alpha, H beta, the location of the star forming branch, at least in the BBD diagnostic diagram. Some of these studies, like from Buff et al., based on Galform, Garg, based on SIMBA, they also looked into the evolution of the O3 over H beta ratio from low to high redshift as observed in some studies like that of Steidel et al. And now with our method, we can additionally capture the location of other galaxy types like composites, AGN, shock-dominated, post-HGB-dominated galaxies in the BBD diagram, follow their evolution. And we can also capture nicely classic calibrations for star formation rates, AGN luminosities, and metallicity. So we're getting these strong line ratio oxygen abundance relations, as, for example, observed in studies by Kurti. Now, thanks to James Webb, we can now extend this type of comparison and validation out to higher redshift, right? So here you can now see the predicted O3 line luminosity function for redshift 7 and redshift 8. So predicted by Sphinx, TSON, Jaguar, which is just an empirical model, flares, and also our method applied to the Santa Cruz SAM compared to new fresco data. So this is actually taken from a recent study of Maya et al. And now what you can see is that there's a generally, I think, given the simplicity of the modeling, good agreement between simulations and observations, perhaps with the exception of TSON, which tends to, underestimate the number counts of O3 emitters by like half an order of magnitude. Okay? But overall, these type of methods seem to be a well-working basis predicting, to some extent, realistic emission line properties, such that we can go now a step beyond and try to explore emission line diagnostics for high redshift galaxies, which are still not very well understood. So let's first focus on HEN. So how can we robustly identify HEN where we're not having a clear broad component, and how can we estimate corresponding properties like luminosities? So here, for simplicity, let's just now focus on our emission line catalogs based on TNG. Let's first look at BPD diagnostics at high redshift. So we have actually already predicted before James Webb that HEN and composites at early epochs move more towards the star formation dominated regime due to generally lower metallicities, which is actually weakening the nitrogen 2 line. This has been nicely confirmed now with new James Webb data, but this implies that for metallicities roughly below 1/3 of solar, these type of classic BPD diagrams are not really useful anymore, right? Instead, for metal-poor galaxies, UV emission lines can become very prominent. They have been observed in many galaxies with James Webb, and there have been a number of different studies also proposing different UV diagnostic diagrams where we can again select composites and HEN. So we also did that with our framework, so based on TNG. So you can see kind of a summary of our best working or most promising UV diagnostic diagrams, for example, carbon-3 over helium-2 versus carbon-4 over carbon-3 versus oxygen-3 over helium-2, where we have, again, a nice separability between these galaxy types. We also try to identify some selection criteria shown here by the black dashed and dotted lines by maximizing purity completeness fractions of these different galaxy types. And I should also add that star-forming composite and HEN are actually defined according to their theoretically predicted black hole accretion to star formation rate ratio. Okay? Now there have been also proposed a few newer UV diagnostics, like which Hannah also mentioned, where we are also in the process to explore them when actually connected to the simulations. We have validated these type of selection criteria against pre-James Webb data, and also they are consistent with a few broad line HEN, which also show these higher ionization lines like GNZ11 or few Sears data. And as Hannah also said in her talk on Monday, some of these diagnostics, which are highlighted here together with others, they were actually used in a study by Jan Scholz to identify type 2 narrow line region HEN, which are actually shown here by these light green symbols. Okay? Now with this theoretical framework, we can actually go beyond just like selecting HEN, right? So we can also try to find diagnostics for other properties. So we find, for example, that optical and like O3 and H beta, and also high ionization UV line luminosities like carbon-3, helium-2, carbon-4 are tightly related with HEN luminosities, as you can see here. So the red thick line is showing a fit to our HEN populations above redshift 3. And some of these relations, they have been used in the recent study by Jan Scholz. They were applied to the identified sample of type 2 HEN in shades, and here you can see the resulting bolometric luminosities versus redshift. You see they're mainly moderately luminous, as we would probably expect for these comparably low mass galaxies at higher redshift. Now beyond that, we've also tried to get some easy estimates for the relative growth of the black hole and the galaxy, so for the black hole accretion to star formation rate ratios. Also here we came up with a few line ratios like N2H alpha, carbon-4 over helium-2, carbon-3 over helium-2, which seem to be well correlated with this ratio. So I have applied some of these relations also to a subset of type 2 HEN in shades, which I got from Jan. Here you can see these ratios plotted versus redshift and galaxy stellar mass. Of course, it's low statistics. We're not finding any significant dependencies here, but you can see that these ratios are pretty high, right? Overly high compared to what we would expect from local black hole scaling relations, so with values above roughly minus 2.5 in log. Now, despite these diagnostics hopefully being somewhat helpful and useful, I'm getting the question, the fair question, how reliable and robust are these diagnostics? Meaning, how much can we trust the results when you apply them to observational data? So certainly, there are some caveats, for example, related to the helium-2 line luminosity, where we know for some extreme cases, for very metal-poor galaxies, that can be underestimated. This is a problem of all currently existing photonization models, but it should be alleviated soon because Stefan Chalot, a collaborator of mine, he has been now developing new binary star models. We will soon have new grids of photonization models. With that, we can revisit this type of diagnostics. Another uncertainty and caveat which we may have in this modeling is how we actually, what we assume for the HEN incident ionizing spectra, right? So at the moment, we're just, assuming a broken power law is shown by the gray line here with a fixed shape, just scaling up and down according to the HEN luminosity predicted by the simulation. But if we look at accretion disk theory and also quasar spectra in the nearby universe, as for example shown in a study by Kubota and Dan 2018, then these spectra can be way more complicated depending on a large variety of parameters. So we have been now using some empirical calculations from this empirical relations from this study and also fixed some of the parameters such that we get spectra mainly dependent on black hole mass and the Eddington ratio. And if you now look at the green lines here, you can see when we go to lower black hole masses, we have a harder ionizing radiation due to a generally smaller and hotter accretion disk. And at a fixed mass, we also find that we have relatively less UV photons compared to X-ray photons, so the radiation coming from the hot X-ray corona. And now, of course, you may wonder, how may this affect narrow emission lines and line ratios? So Adele Platt, she's a postdoc in my group. She has now been constructing for these HEN spectra new large grids of HEN photonization models, which I coupled to the simulations by matching black hole mass and the Eddington ratio to the predicted values to see how diagnostics change or do not change. So let's first have a look at optical black hole diagnostics. So just at low redshift, so you can see they're still roughly falling onto the region as we would expect. The composites have somewhat larger scatter. They are extending now out to higher N2/H alpha ratios, which I think is because we're now also including the harder ionizing radiation for lower mass black holes, right, which can actually boost the nitrogen 2-line luminosity. But here for the HEN, I think we're nicely filling the entire space as observed by SDSS data. Now, when we turn to UV diagnostics, it's interesting. If we just consider diagrams, including line ratios, we're not finding a big difference, right? So these, our previous selection criteria seem to still hold, as you can see here for these three examples. Whereas instead, if we consider diagrams where we have the equivalent widths included, then the location of HEN and composite can change. In particular, it's shifted towards higher equivalent width of UV lines. And again, this makes sense because if we have harder ionizing radiation from lower mass black holes included, which are perhaps more prevalent at high redshift, then this boosts UV line luminosities and therefore increases corresponding equivalent width. Now, turning to relations between line HEN luminosities and line ratio and black hole accretion rate ratios, which I've shown you before, they persist also with the new HEN spectra, and encouragingly, only the slope or the normalization changed very slightly. So I'm in the process of writing this up, but if you're interested in some of these diagnostics, I'm very happy to provide them even before publication. At the same time, we're also working towards a more, complete modeling of HEN spectral signatures by also computing grids for line emission from the broadline region, adding HEN continuum, and some geometrical effects when applying to the simulations. This is also work done at the moment by Adele Platt. And she's also in the process of generating new emission line model grids specifically for super Eddington accretion using or following ionizing spectra for slim disks proposed by Kupota and Dan 2019. And so that the idea here would be to see whether we can find some simple diagnostics which could perhaps allow observers to distinguish, again specifically for narrow line region HEN, whether these objects are accreting at sub or super Eddington accretion, which might provide some explanation of why some of these, high redshift HEN are X-ray faint or even undetected in the X-ray. And thank you. And so with this general framework, the plan is actually to select HEN and estimate luminosities as done in simulations as done in observations, in this way to get really, robust constraints on uncertain black hole models adopted in simulations, which can cause this huge scatter, for example, in HEN number density shown in this comparison plot at redshift 5, taken from a recent study by Abu Zaid. So with that, I conclude the HEN part, and now for the last 5 minutes or so, I will turn to ionization ISM conditions in high redshift galaxies, what we can learn from simulations, and also how to best derive metallicities. So I think an interesting result from James Webb was also that they showed this continued trend of increased line ratios in O3 over H beta, O3 over O2 for galaxies above redshift 4, what you can see here by the pink symbols taken from Chades and Sears. And observationally, what's really causing these elevated line ratios compared to like local galaxy populations, still somewhat debated, whether it's related to increased electron densities or higher ionization parameters, some alpha enhancement, and so on. In the simulations, we capture these elevated line ratios very nicely. You can see that here for TNG. And we find two main ingredients, reasons for causing this. On the one hand, a higher ionization parameter in higher redshift galaxies, which boosts the O3 line luminosity. On the other hand, dust processes are crucial, which can attenuate H beta O2 more strongly compared to O3 because they're closer to the Lyman limit. And also, even though oxygen is depleted on metal grains, it's a major coolant, so this rises the electron temperature. And since O3 is a collisionally excited line, we have a higher O3 line luminosity, which is also boosting these ratios. Instead, we find little impact of the electron gas density and also of the alpha enhancement. We made a test for a scenario where we did not allow the ionization parameter to really evolve above -3. But assumed a very strong form of alpha enhancement. You can see that by no means we're getting these elevated O3 over H beta ratios as observed. Now, very quickly, given that we have likely, strong ionization conditions in high redshift galaxies, as we've already heard also in Alice's talk today, this may change ISM diagnostics like for metallicities. So we have also explored that with our theoretical framework. You can see that here exemplarily for R3 and R23, where we find a strong evolution of these metallicity calibrations, but encouragingly when compared to new James Webb data, where the oxygen abundance is estimated via direct temperature method, we find a fairly good agreement, which actually motivated us to provide fits to our metallicity calibrations above redshift 3, shown here by the red thick line. And we did that not only for these two strong line ratio metallicity traces, but for a variety of other optical and UV line ratios, which are more or less well related with metallicity. So I don't want to go more into detail here, just want to mention very quickly that one has to be very careful with applying present day or classic metallicity calibrations to high redshift galaxies. So we made this test within our theoretical framework, and we found this can significantly bias, underestimate metallicities at high redshift at a given stellar mass. So again, without going here into the details of the plot, I just want to say that this may lead to a too strong evolution of the mass metallicity relation and would, of course, impede a meaningful comparison between simulated and such observed metallicities, right? So if you want to get robust observational constraints on how the chemical enrichment should proceed in your simulation, then you should better make sure to really compare apples with apples, to really compare something meaningful. So how much time do I have left? 2 minutes? 2 minutes? Okay, because, so I want to very, very quickly. Okay. 1 minute. Okay, so 1 minute is fine. So we are working at the moment also on overcoming some of the current caveats we are aware of in our modeling. And so with a PhD student, Lucy Charret, we have now been developing a new star cluster-based model for emission lines, which we call Lumen, where we try to take advantage of information of very high-resolution simulations like the Griffin simulations. And this, we use this information to statistically sample star clusters and H2 regions in a simulated galaxy, say TNG50, where we can't resolve that. And just to very quickly show you, we have validated this method against statistics of H2 region properties observed in nearby galaxies with funks. And we find very nice agreement, particularly for the Strömgren spheres, so the sizes of H2 regions and the ionization parameter, which is by no means a trivial result. Otherwise, we get automatically spatially resolved emission line maps, and otherwise we are really keeping the same good agreement with, basic observational constraints as we've had with the old method, and even improved good agreement with local metallicity calibrations. And so these are incredibly new results. I just got them last week from Lucy, and I think this is really providing an enhanced framework for making more robust emission line predictions for high redshift galaxies in whatever form this will be. And so I'm just leaving you here with my conclusion slide, and I'm happy to take some questions. Thank you.
Many hands raised, so who's going to take care of the mic there? At the end, Benedetta. Andrea was distracted, so Alice first.
Thanks for a great talk. Thanks. I have a question about the alpha enhancement, because as of now, based on a lot of different lines of evidence in redshifts 2 and 3 galaxies, we have evidence that the stellar populations are young and that they do have alpha enhancement, and based on emission line diagrams, the N2 BPT diagram, the S2 BPT diagram, the O1 diagram, neon, through all these lines, we actually, at least with more empirical photonization modeling, conclude that alpha enhancement is the reason for the elevated line ratio. So I guess I'm trying to understand your statement in regard to this multi-line evidential arguments that we've tried to offer.
I fully understand, so I'm aware of these works and they are great, and that's also why we really try to see in our framework what alpha enhancement actually does. And so to explain, what we have been assuming is that the stellar metallicity is 1/5 of the ISM metallicity, which is already a fairly extreme setting, okay? And so, but with our photonization models, we really find that this is only important for like higher metallicities, okay? As soon as if you go really to metal poor galaxies, it's not making a big difference. But if you are for metallicities above like 1/3 solar or so, there it gets important. And so, for example, to match the Steidel data, we find that for high N2OH alpha, we need alpha enhancement, okay? So I have not shown that because I didn't have the time, but I can show you the plot. It's very obvious that we need their alpha enhancement. But for these like even higher redshift galaxies, redshift 4, there we see alpha enhancement is not doing so much, but it's probably because they are just too metal poor. So this is like, yeah.
Okay, thanks. I mean, if anything, you'd assume that the redshift 4 galaxies would be, more alpha enhanced, or at least as alpha enhanced, right? So that it must be an issue
I agree, there. But the point is, I mean, I have also tried to have an evolving ionization parameter plus alpha enhancement. It slightly increases a bit N2OH alpha, but it's not, I mean, we did this exercise, what I showed you, it's not the main driver for getting this. At least that's what we find. Okay, thank you.
Andrea, I can give you.
I think I like very much the project underlying the Lumen code, essentially.
Yeah, I didn't have much time, unfortunately, to talk
about
but
exactly because of that. So can you go back to the slide? You said there's a good agreement with the H2 regions, but it looked to me that you're finding H2 regions are much larger than what they're observed. So it's about 10 times larger.
So it's not plotted in a good way, I think. I mean, we do find indeed some stringent radii being this large, which might be not fully realistic, but the point is that we also find that our stringent radii peak around 100 parsec, right? So we have, at least statistically, sorry?
Yeah,
we have a bit the tail of very large stringent radii, but at least we also have the peak around 100 parsec, roughly. I mean, I understand, yes. This is, I mean, one uncertainty we still have in this type of modeling is a bit the choice of the filling factor when we compute the ionization parameter. So we try to, you know, get distributions of the filling factor such that we at least get the peak of the stringent radii consistent with what is observed, but I think there can be done more. So by using, again, high-resolution simulations and get more constraints on that and perhaps improve that then, okay?
Please.
Hi, Michaela. Great talk. Thanks. I had two questions first. So the first one was on, you mentioned early on that you assume this sort of constant star formation in the large boxes for the young regions. How sensitive are your results, particularly at high redshift, to that assumption, where we expect maybe rising star formation histories?
This is a very good point. So this is actually something we want to change with Lumen, where at the moment we have also, we assume just a flat age distribution for our sampled star clusters, but there we can really explore like different configurations, like having perhaps younger ages only, like from a recent birth or whatever. And I think, so one caveat, what I have not mentioned during the talk, because I didn't have the time, is that we're not really getting, with this method so far, the observed extremely high equivalent widths, be it in O3 or H beta and so on. And so the hope is, I mean, we know from pure photonization modeling that if we just consider that for a stellar population younger than a few times 10 to the 6 years, then we're getting there, right? So the idea would be that we then also try to have, you know, different configurations for how we distribute the stellar ages among the star clusters and try to see how we then match the equivalent widths as observed.
Should maybe chat with Dan as well about that, because we chatted about that during the coffee break. If I've got time quickly, just the only, so on the Lumen side, you know, this resampling of star particles is, you know, incredibly important. And we looked a little bit like, with that with Perak Garg in Simba, you know, resampling star particles to get these. But, so it's not exactly the same.
No,
but
it's
the
not,
reason,
it's very different.
Okay. The main point I was going to make was that it was incredibly computationally expensive. So I didn't know if you could give just an idea of how expensive this extra modeling is on the forward modeling side with Lumen.
So I mean, yeah, I think it depends also on how optimized your code is. So I mean, Lucy just started to work on that, and I think it takes, of course, longer compared to my simple method, where I'm just taking galaxy-wide properties, obviously. But I think if we do a good code optimization, then it should not take ages, right? I mean, it can still work and run fairly efficiently. At least Lucy, she's getting new plots like within 1 or 2 days. So it's not super time consuming. Is this answering your question? Okay.
Any other questions? I have one. Regarding the relative importance of, you know, light diagnostics dependence on black hole accretion rate and star formation rate. This is super interesting. I'm wondering, how do you account for the fact that the black hole and the stars are spatially located in different regions? They may have differential attenuation, different extinction load. Do you have any idea of how to deal with these complications?
I think that's why we have developed something like Lumen, right? Where we can have that in a more spatially resolved way, and then we can also do different attenuation and so on. I mean, this was just like a first try to see whether we get something, whether we get some tracers who could do the job.
So, but the simulations that you showed were actually placing the ionizing source in the same position, or?
Yes. So
this
we did not consider there any difference in dust attenuation or any, you know, these type of geometrical configurations. So this we did not consider so far. But again, I think this is like a great application for the new method.
Okay, if there are no further questions, let's thank Michaela again for this beautiful talk. And